Welcome to the solutions to the Regents Physics Dynamics problem set, problems 1 through 3. Let's get started with number 1. Why do you have to push harder on the pedals of a single speed bicycle to start it moving rather than keep it moving at constant velocity? What you're being tested on in this question is the difference between static friction and kinetic friction. As you probably know from practical experience, static friction, denoted by Fs, is the amount of force required to just get an object moving, as opposed to kinetic friction, which is the amount of force to keep an object moving. And you probably know from practical experience that it takes more force to keep an object moving than it does to keep it moving. So this way would explain why you have to push harder on the pedals of a single speed bicycle to start it moving rather than keep it moving at constant velocity, because it takes more force to just get the object moving than it does to keep it moving. So this bike is harder to get moving at first and then easier to stay moving due to the difference between static friction and kinetic friction. Moving on to number 2. Suppose the acceleration of an object is 0. So let's highlight that. Acceleration of the object is 0. A equals 0. Does this mean there are no forces acting on it? Give an give an example supporting your answer. All right, does this mean there are no forces acting on it if the acceleration is 0? All this means to have an acceleration of 0, I'll just use this box here as our object, is that the net force is 0. So if A equals 0, F net also equals 0. That's the net force. That doesn't mean there aren't forces acting on the object. For example, we could have a force forward on an object and the kinetic friction acting backward on an object, or the static friction acting on an object, depending on if the object is at rest or moving. If these forces are equal and opposite, such that F equals Fs or Fk, then this object would not be accelerating. It would either be at rest or moving at constant velocity. So there are two conditions in which an object cannot be accelerating. It can be at rest. If that's the case, the forward force and the static friction are equal and you just have not broken the object free from static friction yet. Or if the object is moving, the forward force and the backward kinetic friction are equal to each other and the object is moving at constant velocity. So note, under both these conditions, the object is not accelerating, yet there are forces acting on the object. So we've given an example of that here. There'll be many more examples of that throughout the unit. All right, lastly we have number 3. Let's take a look at that. An 873 kilogram dragster, mass, starting from rest, Vi equals 0, attains a speed of 26.3 meters per second, final velocity, in 0.590 seconds time. Find the average acceleration of the dragster during this time interval. What is the magnitude? So average acceleration is A. What is the magnitude of the average net force on the dragster? It's F net during this time interval. And assume the driver has a mass of 68 kilograms, so they're changing the M value. What horizontal force does the seat exert on the driver? So they just want F. Okay? Let's start with A. They want the acceleration of the dragster during this time interval. Well, given the information in the problem, this sounds like a motion calculation. What do we have? We have VI equals 0, VF, T, and we're looking for A. Sounds like VF equals VI plus AT. 26.3 meters per second is the final velocity. 0 is the initial velocity. A is what we're solving for, and the time is 0.590 seconds. Substituting with units. Solve for A. A is 44.6 meters per second squared. Okay? B, what is the magnitude of the average net force on the dragster during this time? For B, the equation that relates net force, mass, and acceleration is F net equals ma. Substituting, we were told that the mass was 873 kilograms, the mass of the dragster, that is, accelerating at 44.6 meters per second squared as calculated in A. Go ahead and solve for F net. Pause if you need a moment to do so. And we get 38,935 newtons, which we must express to 3 digits. So that would be 38,900 newtons is our final answer there. So we have an acceleration of 44.6 meters per second squared, and the force on the dragster would be 38,900 newtons. Lastly, C, assume the driver has a mass of 68 kilograms. What horizontal force does the seat exert on the driver? Well, the horizontal force, again, would be the net force acting on the driver exerted by the seat. They were told that the driver has a mass of 68 kilograms. And since the driver is attached to the car, it is undergoing the same acceleration that the car is, which is a 44.6 meter per second squared acceleration. So the net force exerted on the driver by the seat to 3 digits would be 3,030 newtons. Okay? So just some simple Newton's second law calculations to start off with here. We had a motion equation finding the acceleration, and then 2 different forces depending on which mass is being accelerated to calculate. Much more to come on this as we do numbers 4 and 5 in class tomorrow.